Welcome to The Explainer. So, today we're diving into something really cool, a new paper that's totally rethinking how AI looks at medical scans. And believe me, this could be a huge game changer for how doctors diagnose diseases.
So, how can an AI see both the forest and the trees in a medical scan? In medicine, this isn't just some cute saying, it's a life or death problem. You need an AI that can see the whole organ, that's your forest, but at the same time, it has to zoom in on the tiniest, most critical details, the trees, like the exact edge of a tumor. If you miss one, well, you can imagine the consequences. All right, so to get why this new stuff is so amazing, we've got to talk about the problem first. The thing is, medical scans are, well, they're a mess for computers. They can be super noisy, the contrast can be terrible, and there are all these weird glitches. It makes it really, really tough for an AI to learn properly and work reliably, say on scans from different hospitals. And this slide just lays it all out, right? You've got this massive conflict. On one side, you need that razor-sharp, pixel-level precision. That's seeing the trees, right? Finding the exact border of a lesion. But then on the other side, you need the big picture, the forest, understanding the whole organ. And for like forever, AI models were good at one or the other. Doing both at the same time? That was the holy grail. So, okay, what did we used to do? The older AI tools, they knew they needed both detail and context. The problem wasn't the goal. It was, well, the way they went about it was kind of clumsy and honestly pretty flawed. Yeah, the old way was this cascaded approach. It's literally like that game of telephone you played as a kid. You'd have one AI, a specialist in finding tiny details, and it would do its thing. Then it would whisper its results to the next AI, the one that's good at seeing the big picture. And maybe that one would pass it on again. It sounds logical, right? Just stack these specialized tools. But there's a huge catch. And here it is, the fatal flaw. That's why the game of telephone always ends up garbled. The paper gives it a fancy name, intermodule information loss. But what it means is simple. Every single time the information gets handed off, a little bit gets lost. A detail gets fuzzy, context gets warped. By the end of the chain, what you're left with is a blurry, compromised mess. Oh, and the whole thing is super slow and costs a fortune to run. So that mess brings us to this breakthrough, a totally new way of thinking, embodied in this model called GSAND. It basically throws that whole sequential one-by-one process out the window. Instead, it asks a really powerful question. What if we could see the world in two completely different ways at the exact same time? Okay, so the first way is what's called Euclidean space. Don't worry about the name, it's just the normal, flat, grid-like world we're all used to. Think of a city map. Everything is laid out nice and neat. And this view is absolutely perfect for seeing local stuff. What pixel's right next to what other pixel. It's how you get those super sharp, fine-grained details. And then there's the second way of seeing things, hyperbolic space. Now, this is different. It's not a flat grid. The best way to think about it is like a family tree. It's all curved and branching. This kind of geometry is amazing for understanding the big picture relationships, the hierarchy. How all the different pieces of an organ connect and fit together to make the whole thing. It's for seeing the forest. And this is the real genius of the GSAND model. It doesn't make a choice. It doesn't pick the city map or the family tree. It uses both. At the same time, in parallel. So while it's looking at the fine details in that flat, grid-like space, it's also mapping out the broad, overall structure in that curved branching space. It's getting the trees and the forests simultaneously. Okay, so let's pop the hood real quick. How does this thing actually work its magic? The whole system is built on three new key parts that work together to juggle and combine the info coming from these two different worlds. All right, these names look a little intimidating, I know, but what they do is pretty straightforward. First, you've got this HighJam thing. Think of it like a smart bouncer at a club. It filters the information coming from both spaces, only letting the good stuff through. Then there's Dusra, which is basically an attention mechanism. It makes sure the model is paying close attention to both the tiny details and the big picture structure. And finally, HiFuse comes in. This is the master mixer. It intelligently blends everything together to create one super accurate final image. And, this is key, it does it without losing any information along the way. No more game of telephone. So that's the theory, and it sounds great, right? But the real question is, does it actually work? Is this dual space thing actually better? Well, the research says, oh yeah, it works. And honestly, the results are kind of mind-blowing. First up, accuracy.
Using a standard measurement called the DICE score, this new model is up to 4.11% more accurate. Now, I know what you're thinking. 4%? That's it? But in the world of medical diagnosis, a 4% jump in precision is massive. That's a huge leap that can make a real difference for patients.
Okay, but this is where my jaw really hit the floor. It's not just better, it is ridiculously more efficient. The model itself, the actual amount of code and data, is up to 96% smaller. I mean, think about that. That's like getting a Formula One engine that fits in your pocket.
And because it's so small, the amount of computer power you need to run it just plummets. We're talking a nearly 99% reduction in computational cost. This is the real game changer. It means you don't need a supercomputer to run this thing. It could run in smaller clinics, in hospitals with tighter budgets. It makes this advanced AI so much more accessible.
Let's just look at the numbers side by side to really drive this home. The old top-tier model, Maginet, got about 87% accuracy and took over 210 GFLOPS of power. This new GSAN model, it hits over 92% accuracy and uses less than 4 GFLOPS. So it's way more accurate while using a tiny, tiny fraction of the energy. That's not an improvement, that's a revolution. So what's the bottom line here? This isn't just another small step forward. This is a huge leap. Because it's so much better and so much cheaper to run, this kind of technology could finally put incredibly powerful diagnostic AI into the hands of way more doctors in way more places around the world. We're talking more accessible, more affordable, and ultimately, better healthcare. And that just leaves us with one final, really exciting question to chew on. This whole dual space idea worked wonders for medical scans, but what else could it be used for? What other huge, complex problems out there are just waiting to be solved if only we could learn to look at them in two different ways at the very same time?